What is the difference between velocity and speed? We often use them interchangeably when we're talking with each other, but there is a difference, a big difference in physics. One is a scalar and one is a vector. Speed is the quantity that is the scalar. Velocity is the quantity that is the vector. An average speed is the rate at which an object is moving. Just like the speedometer on your car, it tells you the magnitude of your rate of change, but it does not tell you your direction. So you could put your car in reverse, move it backward very quickly, your speedometer would still only tell you the magnitude of your rate of change in position. The equation for average speed is just going to be our total distance traveled divided by the total time that we traveled. Okay, and so we already went through the difference between our distance and our displacement in the previous mini lecture. Okay, if you ever forget the equation for speed, just ask yourself, oh, when I drive my car, what is the unit on my speed? Well, the unit on your speed is in miles per hour. A mile is a distance, an hour is a time. So your speed is always going to be a distance over time. Now, speed plus direction gives you your velocity. Your average velocity is your displacement. That's your change in position divided by the time of travel. So your average velocity, we have the velocity, the V here for velocity. I'm putting a little bar over it, which represents the average. The average velocity is equal to your change in position, your displacement, delta x, divided by your change in time, delta t. So your average speed will be your final position minus your initial position over your total time that you've traveled. Depending on your initial position and your final position, your average velocity could be a positive value or it could be a negative value, indicating your direction of motion. Well, now we're going to work through a few examples of velocity and speed problems. Now, you're going to see that a lot in this semester, I don't spend a lot of time going through lecture slides. What I do is spend a lot of time going through examples, how we can take these equations and these ideas and apply them to situations. And so you're going to see me a lot of times modeling how we work through a problem, and that's going to be a big part of our physics class, okay? But part of your job is to follow along with what's being done and see if you can replicate that on some of our engagement checks and some of our homework assignments and eventually on your exams. This is check your understanding of the problem-solving techniques that we need to use in physics as we apply our physics equations to real-world examples. I'm just going to flash up this slide right here. You can always come back to it, this slide as a freeze frame before you move on to watch me work through these problems, because I'm not going to have these words on the screen at the same time as I'm working through the problem.
Suppose I drive a car for 200 miles in 2 hours. So I'm going to say x sub 0 or x sub naught is the place where I start. I'm driving for 2 hours for 200 miles. Then I stop for a total of 1 hour to have lunch. Okay, then I get back in the car and then I drive for another 100 miles for 1 hour before I reach my destination. Okay, and so the question is to calculate our average speed. So speed doesn't really care about what direction we go. We're just looking for a distance over a time. And so our average speed is always going to be delta x, our change in position, over delta t, our change in time. So during this problem right here, my delta x, my change in position, has a total of 300 miles, okay? 300 miles. So that's going to be my delta x here. And then my total time during which I took my trip was the 2 hours while I was driving, then my 1 hour of stopping, and then my 1 hour of driving again. So then my total time for this problem to find my average speed is 4 hours. So then in order to find my average speed, I take my position over my total, or my change in position over my total time that I've been driving or stopping, the total time of my trip. And then I get that the average speed is going to be 300 miles divided by the time it took me, which was 4 hours. So 300 divided by 4, that gives me 75 miles per hour. Okay, so the unit here is a distance over a time. Now let's think about another type of average velocity problem. This, we talked about average speed. We don't care about the direction in which we travel. Now I'm going to talk about an average velocity problem where we do care about the direction of travel. So suppose I'm driving a little remote control car, one of those little battery operated cars, and I drive my car from a position of x, initial position of x is equal to 0.5 meters, and then I travel and stop my car at a position of x equals 3 meters. Okay, that's going to be my final position here. And the time it took me to take this journey was 3 seconds. Calculate my average velocity. So my average velocity for this trip is going to be my final position minus my initial position over my final time minus my initial time. Okay, so my final position was 3 meters minus my initial position, 0.5 meters, divided by the time it took me to take my journey. So I can always set t0 to be whatever time I want. So I'm just going to say that at the beginning of my journey, time was 0 seconds. Okay, and so then the final time would be the total time it took me to take my trip, which was 3 seconds. So I've got 3 meters minus 0.5 meters over 3 seconds minus 0 seconds. So that gives me 2.5 meters over 3 seconds, and that is equal to 0.83 meters per second. I'm going to put a plus sign on there because I know that that is a positive velocity. Positive meaning that I moved in the forward x direction or in the positive x direction. My final x position was greater than my initial x position along the x-axis. So we have a positive average velocity here.
And briefly, we are going to talk about motion diagrams. A motion diagram is a representation of a moving object at successive time intervals. So here we have an example. A bicycle is moving to the left with an increasing speed. Which of the following motion diagrams illustrates this motion? Okay, so at each dot, okay, let's say that each one of those dots occurs at 1 second intervals. So here, t is equal to 0, all these happen at t equals 0. At t equals 1 second, that's where the next dot is. At t equals 2 seconds, that's the next dot. 3, and so on. So which one of these indicates an object that is moving to the left with increasing speed? So we want our vector here representing our motion to be to the left because it's moving to the left with increasing speed. So that's going to rule out A and D here because both of those vectors are moving to the right. So we're looking at, for example, B and C are still in the running. If our speed is increasing, that means that as we progress in time, the distance between consecutive time intervals must be increasing, okay? Because remember that a speed is a distance over time, so if the speed is increasing, that distance per the same time unit has to go up. So we will want to choose the one where the distance between the consecutive dots happening at, let's say, consecutive seconds, that distance needs to be increasing over time. And so here, we see that the distance is large, and then over the next time interval, it gets shorter and shorter. That would be an example of something that's decelerating. For an example of something that's moving to the left with increasing speed, we don't want to choose C, we want to choose B here, because every consecutive time interval, the distance is increasing. If this quantity, the distance over time, gets bigger, that means we must have increasing speed. So we're going to go with question B here. Here's another example of a motion diagram. The position of two blocks at successive 0.2-second time intervals are represented by the numbered squares in the figure below. The blocks are moving toward the right. And the question that we're being asked is, do the blocks ever have the same speed? Okay, so let's start looking up here on top. So remember that every, it's like a still shot that's being taken at every 0.2 seconds. So the motion that's happening up here above our coordinate system between these time intervals, it looks like we are increasing our distance. Okay, so that means that our velocity is increasing. Okay, and then down here, let's see, we're starting right here. Let's call that 0. And then at time 2, let's say that time t is equal to 2 seconds, we've moved 1, 2, 3, 4 units. Okay, and then between 2 and 3 seconds, let's say, we've moved 1, 2, 3, also 4 units. And then between 3 and 4, we're moving 1, 2, 3, 4 units. So we know that on the bottom here, the distance between consecutive time intervals is the same, but on top, our distance between consecutive time intervals is increasing. So do the blocks ever have the same speed? We could say no, or at a couple of different instances. So let's look at these here. So we know that between all these consecutive time intervals on the bottom, the unit distance between them is 4 meters. Remember, the speed is the distance over time. Our time is going to be the same across all of these time intervals, okay? It's the distance on top that might change. So on the bottom, all of these are going to have the same speed, essentially, as we're moving between different points in time. Okay. On top, our speed is increasing because the distance is getting larger per time. Let's see, up here between 1 and 2, the unit distance between them is 1, 2, 2. Between 2 and 3, our unit distance between them is 1, 2, 3. And then here, between 3 and 4, our unit distance between them is 1, 2, 3, 4. Okay, so between 3 and 4 here, and between 3 and 4 here, we do have the same speed. They're both moving the same unit distance in the same time interval. So let's check to see if there are any others that might work. Between 4 and 5, on top here, we're going 1, 2, 3, 4, 5 units. So that doesn't equal the speed that we have on the bottom here, and the distance just keeps on getting larger between the consecutive intervals on top. So then, do the blocks ever have the same speed? Yes, they do. At instance, oh yes, at some time during the interval between 3 and 4 would be the answer here. Yep, only here is where we have the same change in position over change in time. If velocity is the rate of change of your displacement, then we have something that represents the rate of change of your velocity, and that thing is called acceleration. Acceleration is the rate at which your velocity changes. Acceleration is also a vector, so it has a magnitude and a direction. The sign on the acceleration tells you the direction. So here's our equation for average acceleration. The bar on top of it denotes average. Average acceleration is equal to your change in velocity over change in time. So that's your final velocity minus your initial velocity divided by the total time that you traveled. If the acceleration is in the same direction as the object's motion, then that object is speeding up. If the acceleration is in the opposite direction of the object's motion, then that object is decelerating. It is slowing down. So here are 2 examples of objects that are accelerating. Here we have a car with an acceleration vector in the positive x direction. Its velocity vector is also in the positive x direction. And so because those are both of the same sign, it is accelerating. Okay, its rate of change of velocity is increasing. Here we have a car that has a negative acceleration. It also has a negative velocity vector. It is moving along the negative x-axis, okay? And because both of these have the same sign, that means that our acceleration is in the same direction as our object's motion. Even though both of those vectors are pointing in the negative x direction, this object is accelerating. Its rate of change of velocity is actually increasing. So let's say over here at this point, maybe it has a velocity of minus 100 meters per second. But over here at this point, it had a velocity of minus 50 meters per second. So the magnitude of the velocity, the speed, is increasing over time just in the negative x direction. That gives you a negative acceleration. Okay. So this object we would consider to be accelerating, meaning that it is speeding up. Now these two objects are decelerating. They have velocity vectors that are opposite of their acceleration vectors. That means that their rate of change of velocity is decreasing. Essentially, something's happening, like somebody's putting their foot on the brakes, or there's drag there. Maybe they open a giant parachute behind the car to make that car essentially the magnitude of the velocity, its speed, to make that speed decrease over time. So if the velocity vector is opposite in sign of your acceleration vector, then that object is decelerating, meaning it is slowing down over time. So now we're going to practice those ideas by working through a few example problems about acceleration. And here's the still shot of those questions that I'm going to be asking as I work through those problems next.
Suppose you are drag racing. Here's our car. And 5 seconds after the race starts, your car is moving at 40 meters per second. So I'm going to call that T0 is equal to 5 seconds, and then V0 is equal to 40 meters per second. Okay? 60 seconds after the start of your race, you have reached 150 meters per second. So at some later time, which is 60 seconds, your velocity at that time is 150 meters per second. What is your acceleration? So the thing that we're looking for is acceleration, or what is your average acceleration? So let's put a little bar over there to represent that this is going to be an average acceleration. Okay, so we don't know if we're having a constant acceleration during this time. We only know one initial starting point and one final point. Okay, so the equation for average acceleration is our change in velocity over our change in time. Okay, so then this is going to be v final minus v initial over t minus t initial. Okay, now something that I really want you to pay attention to when you're working through these problems is that whenever we work out a problem, and I'm not always going to explicitly say this, but we always want to identify our knowns. Those are the things that I wrote up here. These are the things that we know. Our unknown, the thing that we're trying to solve for, and we want to start with an equation. Okay, an equation, especially if I were making you take this class and do a written, fully written exam, I would always ask you to start the problem on your exam with an equation that comes from your equation sheet. And you need to write it out sort of in this algebraic form here. Then once you have that, then you can fill in the numbers. Maybe even you have this, you could even maybe solve it for an unknown if the unknown that you're looking for is not what it's already equal to here. Then you can put in your numbers to get your final answer. Okay, so we want to identify our knowns, our unknown, find an equation, stick those numbers in, then we get the final answer. Okay, so the answer is the very last thing that we're going to get. So here I'm going to go ahead and fill in what my final velocity was, 150 meters per second, minus my initial velocity of 40 meters per second, divide that by my final time, which was 60 seconds, minus my initial time, 5 seconds. And so then, if I take 150 minus 40 and divide it by 60 minus 5, I get that my average acceleration over this time is 2 meters per second squared. Okay, the units on an acceleration is a distance over a time squared. Always an acceleration has a distance over a time squared. Where do we get that from? Well, let's see. So we have a meter per second on top, and we're dividing it by a second here. So this looks like, if we're just thinking about something called unit analysis, where I just look at my units and see if they make sense, I've got meters per second divided by a second. Okay, so I can think of this as being like a meter per second divided by second over 1, because you can always make a fraction by taking something and putting it over 1, okay? And so whenever I divide by a fraction, I multiply by the reciprocal. So this looks like meter per second times, if I'm dividing by the fraction, I multiply by the reciprocal, so times 1 over second, okay? And so then I've got a meter and then a second times a second on the bottom. So that unit is meters per second squared. So that's where my unit comes from on acceleration. Okay, so that's for this problem. We have our velocity in the positive direction. Our velocity is increasing over time in the positive direction. And so that means that our acceleration is positive. And so our acceleration vector is also pointing in the same direction as our velocity.